Welcome to lecture number 26 of ECE 463-663 Modern Control. Today's topic is multi-input, multi-output controllers designed using LQG methods when you have servo-compensators. Now the problem I want to look at is going back to the apartment complex we looked at 2 lectures ago. Suppose I had a 6-apartment building and I want to control the temperature in the different apartments. With one input, I can control one output. If I have n inputs, I can control n outputs. I'd like to do that, control the temperature and n outputs using servo-compensators. So let's start with the first case. Suppose I have a single input. I've got 6 apartments. If I force all apartments to have the same amount of heat, so I have this one matrix on the B side. If I have 100 watts going to apartment 1, all apartments have 100 watts of heat going in. With a single input, I can only control a single output, so I have to pick what I want to control. Arbitrarily, let's control the temperature in apartment 2. Now I could do something different. I could do the average temperature. I could control apartment 1. Just for illustration purposes, let's control the temperature in apartment 2. If I do that with a servo-compensator, what I do is have my dynamics. I've got the disturbances from the outside. I've got my output, that's apartment 2. I'll compare it to my set point, which would be 70 degrees Fahrenheit, and then I'll integrate. Take the integral of the difference between the two and feed that back to my feedback control law that finds U. The challenge is find the feedback gains Kx and Kz to stabilize the system. And I'll be using LQR methods to do that. Now, if I do that, set up the A matrix, the B matrix, the C matrix, create the augmented system. Here's your plant plus the servo-compensator and integrator, where the input is state number 2. I want to control the temperature of state number 2. I'll get my feedback control gains using LQR methods. Again, this is just one way to find feedback gains. If I want to find out how does this behave in steady state, if I make my set point 70 degrees and find the DC gain, I'll see that sure enough the thing I'm controlling is 70 degrees. The other apartments are a little bit different. That's due to your feedback control law. This last state minus 17, that's my servo state. I don't really care about that last state, that's a dummy state. But all the apartments are close to 70. The one I'm controlling is 70. And with a single input, I can only control a single output. If I include the disturbances, then what happens is I'll take the DC gain of the system relative to the set point of 70, add to it the disturbances of, say, 10 watts of heat coming in from apartment 1 and 4 from the sun. What happens is, again, what I'm controlling is 70 degrees. With the servo-compensator, I'm forcing the output to track my set point. Apartment 2 is 70. Problem, however, is that the people in apartment 1 and 4 are sweltering because the sun's coming in, and I'm applying heat because apartment number 2 wants the heat, even though apartment 1 and 4 don't need it. That's a problem when you have a single input, single output system. With a single input, I can only control one output. Let's see. Suppose now I have 2 inputs. With 2 inputs, I can control 2 outputs. So arbitrarily, let's assume the first floor, all the heaters are tied together, and the second floor heaters are all tied together. With 2 inputs, I can control 2 outputs. So let's control the temperature in apartment 2 and apartment 4. Again, using LQR techniques, I can do that. Design the servo-compensator. In this case, I'll have 2 servo states. The integrator controlling the temperature in apartment 2, integrator controlling the temperature in apartment 4. I've got a double integrator, my 2 inputs, first floor and second floor. Put it all together, here's the augmented system. Using LQR techniques, I can then find the feedback gains. An advantage of LQR, I have 2 inputs. I now have 8 states. I have 8 feedback gains. I can look at the steady state behavior. If I say apartment number 2 should be 70 degrees, apartment number 4 should be 80 degrees, look at the steady state values, and sure enough, apartments 2 and 4 are right where I set them. That's what property you have. When you have 2 input systems, I can control 2 outputs. With servo-compensators, I force the DC gain to 1. Those outputs will go and track your set points. The other apartments are off, however. I'm not controlling them. They're just wherever they wind up. And the last 2 states are the servo states. I don't really care. Those are dummy states. If I have the sun shining in, I can see the effect of the feedback gains plus the disturbance. I wind up with apartment number 1 is sweltering. Apartment 4 is still 80 degrees. The servo-compensator will reject a constant disturbance, track a constant set point. Again, those 2 will be dead on. Everyone else is kind of out of luck. Third option. Suppose I want to have 6 inputs controlled separately. In that case, I'll come up with 6 servo-compensators. This is 6 integrators, forcing the temperature in each room to be my desired temperature. I'll now get a 12 by 12 system. There's 6 plant states, 6 servo-compensator states. And I'll wind up with a 6 by 12 matrix, 72 feedback gains. And that's just kind of how LQR techniques work. I get full state feedback. If I want to look at the steady state response on a cloudy day, when there's no disturbance, if I arbitrarily set the set points to 60, 65, 70, 75, 80, 85, you can see that the temperatures are dead on. And the servo states are wherever. I don't really care about the servo states. Again, there I can track a constant set point. If I have a constant disturbance, the sun shining in, again, the temperatures are dead on. When I have 6 inputs, I can control 6 outputs. The disadvantage of this method is right here. With LQR techniques, I wind up with 72 feedback gains. If I want to set certain gains to 0, too bad. When I use LQR techniques, I'm going to wind up with a full matrix, all 72 feedback gains. But with that, that also illustrates the principle. If you want to control n outputs, I need n inputs. And with servo-compensators, I can force the DC gain to 1 for each of those outputs.